So lately we've been talking a lot about similarity and triangles, and obviously one of the big concepts that's wrapped up in all of that is the idea that the corresponding sides of similar triangles will be proportional. What we're going to look at today in this video is how there's some proportional relationships within perhaps a single triangle if certain things were to happen with that triangle. So that's what we're going to be looking at today. Let's jump right in. Now, the first of the theorems that we're going to look at is called the SIDE.SPLITTER theorem. The SIDE.SPLITTER theorem sounds like it would maybe be something that's supposed to be funny, you know, like when you're laughing so hard you split your sides. I guess that's a phrase. I don't know. But this one's, I guess, not really funny. It's just that it's kind of describing what's happening in the situation. What we're doing in the SIDE.SPLITTER theorem is we're taking a line parallel to one side of a triangle and using that line to intersect the other two sides. So you can see we have segment MN, which is parallel to segment AC. We can see the mark showing that it's parallel, and it's intersecting the other two sides of my triangle ABC. When that happens, it's going to divide the two sides that it intersects proportionally. So segment AB and segment CB have been divided proportionally by segment MN. And what that means is, if we divide two segments proportionally, it means that if we make a ratio of the two parts on segment AB, so we make a ratio that says AM over MB, that ratio would be equal to the ratio that we make over the same parts on the other side. So we put AM, which is like the bottom part of this side, over MB, which is the top part, and then we said that that ratio would equal CN over NB, which again is the bottom part of the other side over the top part of the other side. So this idea right here is what it means to say that this segment has divided these two sides proportionally. Now this is a theorem, which means it can be proven to be true, and so I'm going to take a few minutes here just to kind of show you the proof of how this ends up being true. And it actually goes back to the idea of similar triangles. Because if we look, what we have is we have two triangles, triangle MBN and triangle ABC. MBN and ABC. Those triangles are going to be similar to each other by angle. I'll show you what I mean. Triangle MBN is similar to triangle ABC by angle similarity, because they both use angle B, and then this angle here and this angle there are going to be congruent because they are corresponding angles created by parallel lines and a transversal. So we learned way back when in the second chapter that those corresponding angles would have to be congruent. So there's our two pairs of congruent angles, and that means our two triangles are similar. And if those two triangles are similar, that means that if I could make a couple proportions, like if I take AB over MB, that would equal CB over NB. So this is just a statement saying that AB, which is this side of the larger triangle ABC, paired up with MB, which is the corresponding part of the smaller triangle, that ratio equals CB over NB. And that just stems from the idea that the triangles are similar, which means that their corresponding sides will be proportional. And then from that, what we're going to do is we're going to, instead of saying AB, we're going to break that into its two parts, AM and MB. So now I'm going to take that statement and turn it into AM plus MB over MB. And I'm going to do the same thing with segment CB. I'm going to say NB plus NC over NB. And so all I did is take this statement and break AB into its two parts that I see in the picture, and do the same thing with CB, break it into its two parts. Now I'm going to cross multiply this proportion. And so when I cross multiply, it looks like this. I'm going to have MB times NB plus MB times NC. So this is just taking MB times both, basically distributing this MB into this kind of numerator right here. So MB times the NB and MB times the NC. And then I'm going to do the same thing with NB multiplying times this numerator. And so that's going to give me NB times AM plus NB times MB. And what I'll notice now is both sides have this term, MB times NB, MB times NB. So I can essentially cancel it out, leaving me with just MB times NC equals NB times AM. So I canceled these out. And then from here, if I take this side and this side, divide them both by MB, and then I take both sides and divide them both by NB. So I'm dividing both sides by this and then dividing both sides by that. Okay, and I'm starting to run out of room here a little bit, so I'm going to kind of bring this up here. I'm taking the MB times NC side, dividing it by both MB and NB. And then I'm taking the NB times AM side and dividing them both by the same two things. What's going to happen is cancel, cancel, and I have NC over NB, or I'll write it as CN over NB. Cancel here, I have AM over MB, and that is what I was trying to prove always happened. So it's a little bit of a lengthy proof using some kind of like algebra basically, but it shows that it all stems off this idea that when I take this segment in here, put it in here parallel to this side, it creates my two similar triangles, and then from that idea I can kind of do some fancy algebra to turn into it to get a statement that says that these two ratios are equal. Now our next theorem is called the triangle midsegment theorem. We've talked about midsegments before when we talked about trapezoids. We said that a midsegment in a trapezoid joins the midpoints of the two legs of the trapezoid, and we're going to have something similar with the midsegment on a triangle. It says if a segment joins the midpoints of two sides of a triangle, that means that's what a midsegment's going to do. It's joining, in this picture we see G is a midpoint of this side, dividing it into two equal parts. H is a midpoint of this side because it divides it into two equal parts, and then we've joined those two midpoints together. So this thing right here is our midsegment, all right? So I'm going to just kind of label it here. That is the midsegment of one of the midsegments technically of this triangle. When we have that, that segment will be parallel to the third side. It'll be parallel to DF, and it'll be half as long as DF. So GH is half as long as DF. And so when I have that midsegment, it's going to be parallel to the third side and half as long. Now the proof for this is a little bit quicker. I'll kind of run through the proof pretty quickly. Basically what we have is, again, that triangle GEH is similar to triangle DEF by, in this case, it's side angle side similarity. And I'll just, instead of writing that out, I'll just show you how a side angle side works. I have an angle right here that's used in both triangles, so there's my angle pair that's congruent. And then if you look at the sides on this side of it, the long side is clearly twice as long as this side in the smaller triangle. So my bigger triangle, this side is twice as big as that one here, and then the same thing happens on the other side of that angle. The bigger triangle's side is twice as big as the same side on the smaller triangle. So that SAS similarity is going to work here because these two side pairs are proportional, and I have this included angle that's congruent. Since these corresponding sides are half as long, right? EH is half as long as EF, and EG is half as long as ED, then that means the third pair of sides will also have that same relationship where GH is half as long as DF. Right, so I'll say, to kind of come back over to my proof here, I'll say with a scale factor of 1/2. All right, so that indicates that all the corresponding sides of the smaller triangle are half as long as their corresponding side on the big triangle. So that takes care of this part, that GH is going to be half of DF. But how do we know that they're parallel? Well, when the triangles are similar, then their corresponding angles will be congruent. So that means that this angle here and this angle here are going to be congruent because the corresponding angles, they are corresponding angles within the two similar triangles. They're also now corresponding angles for these two lines and this transversal. And so when those corresponding angles are congruent for two lines crossed by a transversal, then that tells us that those two lines are parallel. So I'll kind of add to my proof here. I'll say that GH is parallel to DF because corresponding angles are congruent. And this is a pretty shorthand version of the proof of why this works, but it kind of gets the idea. So that's called the triangle midsegment theorem. And then the next thing we're looking at is actually kind of, it's not its own theorem, it's what we call a corollary to the side splitter theorem. And a corollary just says it's like something that we would be able to say is true based on the fact that this other theorem is true. It's not necessarily its own theorem, it's just kind of like, well, if this is true, then that would kind of mean that this other thing is going to be true. And so what this one says is, well, basically pretend that we, instead of having a triangle where we have some parallel line, lines parallel to one side of the triangle, we just kind of tilt that line up, and so now we just have these two lines. And they're going to cross over three parallel segments. So we got line L, line M, and line N. Three parallel lines, I guess I should have said, crossed by two different transversals. When that happens, the segments that are what we call intercepted on the transversals are proportional. So the fact that I have these three lines, and then I look at this one transversal right here, those three lines are cutting out two segments from this transversal, segment AB and segment BC. They're also going to cut out, those three parallel lines are going to cut out two segments on this other transversal. They're going to cut out segment DE and segment EF. According to this idea, when I make a ratio of AB over BC, when I make a ratio out of those two segments, it should be equal to the ratio for these two segments, DE over EF. And again, that's just coming off of the idea of the side splitter theorem. So again, three parallel lines, a transversal on one, like basically two transversals cutting across those three parallel lines. And every time one of those transversals cuts across it, we get these two segments that are created, here, here, and here, here. Those segments ratios are equal to those segments ratios right there. Now finally, we have one more theorem called the triangle angle bisector theorem. And this one's a little bit wordy. It takes a minute to kind of wrap your head around what it's saying. But basically what it's saying is if I have this triangle and then I bisect one angle of that triangle. So I have this ray that's coming out here cutting this angle into two equal parts. That ray will also cross through the third side of the triangle, right? So it's bisecting this angle and then it's continuing on through, crossing through this side, breaking it into two parts, UX and WX. There's a relationship of proportionality between these two parts and then the other two sides of the triangle. And it says that it's this third side of the triangle is divided in a way that's proportional to the two sides of the triangle that makes the angle that got bisected. So ratio of UX over WX is equal to the ratio of UV over WV. So these two in a ratio equal these two in a ratio. And that's called the triangle angle bisector theorem. Now I'm going to run through the proof of this real quick. It's kind of a neat proof, actually. It's neat because what you have to do to prove that this is true is you actually have to add to this drawing, which is something we have to do sometimes when we're trying to prove that a statement is true. So the first thing I'm going to do is I'm going to add a line that is parallel to VX. All right, so I'm going to add this line here, and I'm going to say it's parallel to this one. So I've added this line parallel to that, coming off of this corner of the triangle. Next, I'm going to extend this side until it meets that line I just created. So I'm going to kind of extend this over, and I'll label that point where it meets, I'll label that as point Z. So what I have now is I have two parallel lines here, and then I have a few transversals going across those parallel lines. Now if I think about the ideas of when I have parallel lines crossed by a transversal, I have some angles that are going to be congruent. For instance, this angle here would be congruent to this angle right here because those would be corresponding angles for two parallel lines crossed by a transversal. So what I'm going to do now is I'm going to put this mark right here. And then I'm also going to put that same mark right here because this angle and this angle would be congruent because they're alternate interior angles. I have my parallel lines here and here, and then I have this transversal cutting through here. So these angles would end up being congruent. So now what we'll notice is that when I added these two lines, it actually created a situation called that the side splitter theorem describes, where I have a segment here parallel to one side of a big triangle, triangle ZWU, right? This segment is parallel to one side of that larger triangle, and so that tells us that ZV over VW should be proportional to UX over WX. So let me write that down. That ZV over WV should be equal to UX over WX. Now, if you look at that statement, it's similar to this, but with one big difference. This one has UX over WX equaling UV over WV, but I have ZV over WV. But if we come up to this picture and we look at this triangle right here, it's isosceles because it has two angles that are congruent. And this side that's ZV, right, this guy right here, and this guy right here should be congruent to each other because this is an isosceles triangle, which means that in this statement, I can take out the ZV and I can just replace it with the UV. So this, since UV equals ZV, then I can say UV over WV equals UX over WX. And that's how I prove that this is true. So I just wanted to run through that proof because it's kind of cool because we add some things to the diagram to actually prove what happens in this theorem. So there you have a few different theorems that are all kind of dealing with one single triangle and some proportional relationships that might exist at times within those triangles.